Hello everybody, this is Professor Lombardo. Our last example here that I want to show you uses the binomial distribution in kind of an interesting way. We're going to use our binomial distribution to test an assumption. So here's our basic setup. We're going to work off of our W5 D2 workbook, and we're going to go to the last tab, which is our testing assumptions tab. So here's the setup of our situation. We have 4 different designs that we can choose from when we're going to release a product. Design 1, Design 2, Design 3, Design 4. Okay? We want to decide which one of these designs is going to be the best. And we're consulting with a colleague, and they make the claim that it doesn't matter, just pick whichever one's cheapest because the designs are more or less the same. So there aren't going to be any preferences in the population for one design over another. Now, we personally don't feel that that's true. And so what we want to do is use some actual data and some probability analysis to show that that is not the case. Okay? So here's how we're going to do it. What we're going to do is kind of play devil's advocate. We're going to assume that our colleague is right. We're going to assume that out in the population, there's absolutely no preference between Design 1, Design 2, Design 3, and Design 4. In other words, what we're going to assume is that if we focus in on a particular design, let's say Design 1, this should have a 25% chance of being selected. Okay? So what this chance that we're assuming here, we're playing devil's advocate, that 25% chance we're going to use as our probability parameter in a binomial distribution. And then what we're going to do is go out into the population and we're going to create a sample, much like the one we have here in the cells A2 to D201. Here we asked a whole bunch of different people what their design preferences were, and we recorded their answers. Okay? Now here's what we're going to do. We're going to use our binomial distribution where we assume that our colleague is right. There's no preference between the designs, so the probability that somebody would choose design 1 is 25%. And we're going to check, based on the actual counts that we get out of this, out of our survey, we're going to check, is that kind of in line with what our binomial distribution would have predicted? In other words, is the score that we get, is this in the usual range of scores, or is this sort of outside? Is it something unusually high or unusually low? So in order to do this, what we need to do is, first of all, consider how many people we sampled in our survey, because that's going to be the same thing as the n value for our binomial distribution. Since we're dealing with text, right, design 3, design 2, design 1, etc., we need the COUNTIF function. We can plug in our range, and the criteria we're going to use to count up all the cells is, remember, the little asterisks inside of your quotes. So this indicates that we've interviewed 800 people and asked them what their design preferences are. Okay? So in our binomial model, where we're playing devil's advocate, we're assuming that our colleague is right. There's no preference between designs, so the probability design 1 gets selected is 25%. We've asked 800 people, right? This is going to allow us to answer questions like about our certain probabilities. Okay? Now let's go back into our sample and let's count up. So COUNTIF from A2 to D201. Let's count up how many of these people actually preferred design 1. So we'll type out design 1, make sure it's spelled correctly, put it inside of our quotes, and we can count this up. Right? So out of the 800 that we sampled in our survey, 225 ended up preferring design 1. Now the question is, the underlying question is this count, is what we observed, is this thing really in line with the binomial model that we're assuming when we play devil's advocate with our colleague? Okay, so in other words, is this kind of in the range of usual values? So if we're looking at whether this falls in the usual range of values, it helps to compute the mean and the standard deviation of the binomial model that we're assuming. All right. Now we have formulas for this, and so I'm just going to, I put the formulas on the side here. N times P ends up being your mean, so I can do 0.2, your N is 800 times 0.25. This should give us our expected count of how many would prefer design 1, assuming, again, our colleagues claim that all the designs are the same, so only 25% of the population would like design 1 the best. Our standard deviation, we compute using our square root of n times p times 1 minus p. So we get 12. And then keep in mind that your usual range of scores is going to look like your mean minus 2 standard deviations, and then your mean plus 2 standard deviations. So we can compute these just using cell referencing formulas. Here's your mean. Here's minus 2 times your standard deviation, right? And then here's your mean plus 2 times your standard deviation. Oops. Wrong cell reference. This should be K12. There we go. And so the usual range of scores should fall between 175 and 224. So we, with a count of 225 preferring design 1, we are really right on the edge of this usual range of scores. Okay? Now another thing we could do, if we decided to, is we could compute the z-score using these parameters associated to a count of 225. So let's do that. Here's our count. The count that we actually got for design 1 is 225. The z-score that we could look at, this would be our count minus the expected count divided by our standard deviation. Okay? So our z-score in this case is 2.04, which we know, typically speaking, is an unusually high z-score. So that kind of provides evidence that the count we're getting in our sample is refuting his claim that only 25% would prefer design 1. It seems like more would prefer design 1 based on our sample. Okay. Now the last approach, so this is the usual range of values. This is our sort of z-score anomaly analysis approach. The last is where we start taking a look at counts in terms of their definition as being unusually high or unusually low. Okay. If a score, right, this 225, if this count is unusually low, what would happen is if we compute the probability that our x value is 225 or below, this would be a very small probability. Now we can do this with our binom.dist function. The count we're using here is 225. It's already in its cumulative form, so we just have to fill in the number of trials or the number of our n value, our p value, which, playing devil's advocate, is 0.25. And then we would type in true for the last part because this is a cumulative probability. So this is certainly not unusually low for a score because the probability is not below 0.05. Okay? The other option is that you could have a certain count or a score be unusually high. Right? Now in this case, when you're testing for unusually high, you want to find out what's the probability of getting that count or something greater. So here we want the probability x is greater than or equal to 225. When we're dealing with the greater than, we're going to use our usual trick where we start at 1 and we subtract off the values we don't want, which would be 224 and below. So when computing our probability that x is greater than 225, we would do 1 minus binom.dist, and now I'm working off of this cumulative probability here, x less than or equal to 224. So I would do 224. I have 800 trials, 0.25 is our probability of success, and then true, because we're dealing with that cumulative probability. Oops, I have a space in here I need to get rid of, so this evaluates as a function. And we can see that this certainly is less than a 5% chance. So the probability of getting a score of 225 or something larger is way under 5%. It's about 2.3%. So yes, this 225 is considered an unusually high count for this binomial model. Okay? So here's the fundamental question. Does the probability model that we create by taking our friend's word for it that there's no preference between these designs, right? Which led to this particular probability value of 0.25. Right? Does this fit with our observations when we actually went out, collected a survey, and looked at a count of how many people preferred design 1 in this example? And the answer is no. And we have 3 reasons why. Right? First of all, 225 falls just outside of our usual counts according to our empirical rule, right? Moving 2 standard deviations from the mean in either direction. Empirical rule, all right? Our other is no, because 225 has a z-score of 2.04, which is an unusual z-score. So in other words, this is not the type of count we would be expecting, assuming that this binomial model is holding. The one we're going to go to most often is dealing with determining whether a count is going to be unusually high or unusually low. So our answer here would be no, because 225 is an unusually high count for this binomial model. Right? And essentially what this means is observing a count of 225 or something larger has an under 5% chance of occurring naturally, assuming that this model holds. All right? So here's the evidence we provide against our friend. We're like, all right, playing devil's advocate, if there's only a 25% chance that people prefer design 1, right, then we went out, we collected a survey, and we observed that 225 of our 800 people surveyed preferred design 1. Now, if your model is correct, if there's absolutely no preference between the 4 designs, then this would occur randomly with a chance of 2.3%. That's extremely rare. So getting a count this high is extremely improbable. So it's more likely that your original probability estimate here was wrong. Okay? And this is a way that you can use probability models to test claims. If somebody makes a claim like this, 25% of the population likes design 1, what you can do is assume that they're right, and then go collect a survey, get a real count based on that survey, and then test, is this what we would call an unusually high or unusually low score? Because if it is, it provides evidence against their original assumption. Okay?